comfortable for you. So, okay. So basically, tens digit, 10,000. So what do you got? The big number, 734. Yes, let me just write it here. 734,892. They're just giving us a big old number. All right, so we're moving now into whole number, thinking about whole numbers and models with that. I'll explain what I mean by that. So things that represent whole numbers. So first off, let's just talk about the values. We're back to base 10 now. No more foreign for the rest of our days in here. No more foreign bases. It's all base 10 now. So you know how the system works, right? The first place is called the, what's place? Ones. You know it super well now. Tens, hundreds, thousands. You know, this will be the, running out of room here, 10,000s, right? And this is the 100,000s. Because it multiplies by 10 every time because we have a base 10 system, don't we? Okay. That, by the way, is why the metric system is so much easier to use than like English units, because it's all based on 10 as well. Anyway, fits our number system hand in glove. So here's the question. They're saying find the tens digit. So what's the tens digit? Well, it's right there. It's the 9. Find the 10,000s digit. So that's the 3. That's the 3. So that'll be cake for you. For each of the following base 10 numerals, give the place value. So now they're going to go, okay, 5, 6, 9, 4, 7, 9. It looks like they're underlining the 4 there. And they're saying, what's the place there? So it's ones, tens, hundreds. So there's the answer, hundreds place. And then, yeah, so I'm going to skip those down when it gets hard. Okay, so 6 plus 5. Okay, fill in the blank, blah, blah, blah. 6 plus 5. Oops, my 5s always look a little weird. Equals what plus 6? Well, you know this rule. You know that it's just 5 there. And what that's saying is you can switch the order of adding, huh? And you all know that, right? The order of adding never matters. 6 plus 5, 5 plus 6 is 11. Either way you do it. What's that called? Well, there's the name right there. That's called the commutative property of addition. That means you may switch the order. That's called the commutative. Way to remember that. I had a teacher one time that said, it's like when you commute. What does a commuter do? It goes back and forth, back and forth. So that's what we call that, the commutative property. You can switch the order. Now, is that true for adding, subtracting, multiplying, and dividing? Can you always switch the order, or just some of the operations? What's the story with that? We see here it's good for adding, huh? You can certainly switch the order of adding. Any two numbers added, switch the order, same answer, doesn't matter at all. How about for subtracting? Is 6 minus 5 the same as 5 minus 6? No, that's 1, that's negative 1. Not true. So for subtraction, you can't. The commutative property doesn't work for subtraction. How about for multiplication? How about 6 times 5? Is that the same as 5 times 6? Yeah, so multiplication is also commutative, isn't it? Order doesn't matter. You can switch the order. And finally, how about for dividing? Let me do one that works. Like 10 divided by 5, is that the same thing as 5 divided by 10? No, that's 2, and that's a half, really, isn't it? 5 over 10, you know? So it's not true. So for dividing. So for which operations are commutative then? So adding, yeah. So adding and multiplying are commutative, meaning you can switch the order. The order doesn't matter. But for dividing and subtracting, the order matters. Bless you. All right. Good. Moving on down. Down here, they're doing something a little different. They're going to take, let me write it up for you, 7 plus parenthesis 6, or bracket, parenthesis 5 equals 7 plus 6 plus parenthesis 5. That's kind of weird looking. All right. Well, you can see the answer is already, that's the associative property. Now, what does that mean, the associative property? It means which two you associate together first. What I mean is, do you see how the 6 and the 5 are being grouped in brackets together? You would do them first, get 11, then add the 7 for 18. Over here, the 7 and 6 are being associated together first to be 13. Then add the 5, 18. Same answer, doesn't matter. That's called the associative. Now let me help you distinguish them. You might think, whoa, how's that different than commutative? Commutative, the order changes. See how there was no order change? In this one, 7's first, 6's in the middle, 5's last. 7's first, 6's in the middle, 5's last. We didn't change the order on anything, did we? So we didn't do any commutative stuff, but we associated a different two together. Last two or the first two? Associative property. So you can associate different ones together. The associative property on that. Now that works for addition, right? If they're all just added up, sure, that's great. If you have more complex things going on, that might not work, right? Like how about if we had 7 minus 6 plus 5 and 7 minus 6 plus 5. If I put the parentheses, say, around the first two, or I put it around the last two, that's not the same, is it? Because this would be what? 1 plus 5, 6. Funny looking 5 again. I go too fast. 7 minus 1. Oh, wait a minute. Oh. Is it always going to work? I honestly, I'm really not fooling around. I thought that wouldn't work. Oh, wait, I did it wrong. No wonder. It's 11. I'm having a little trouble today. It really didn't work. There we go. That's what I thought would happen. Wow, that was weird. I've discovered a new math law. No. All right. So, yeah. So associative property doesn't always work when you mix in operations and stuff. But this one was just adding all the way. So, yeah, everything works for adding. Associative property worked. There's no relate that so that kids feel that. So first off, subtraction. Let me just start with the blank screen. You probably know that 7 minus 3, subtraction, can be written as adding, can't it? How can I write that same problem as adding? 7 plus negative 3. Yeah, just make it negative. So subtraction is just adding a negative, isn't it? So my point is, subtraction is really just adding. Right? Bless you. So subtraction is just adding a negative. It's the same thing. Or, another way you could say it, 7 minus 3 is 4. Another way you could write that as an adding fact instead of a subtracting fact is you could say, 7 minus 3 is 4. You could say 3 plus what is 7. That's another view of it, right? Subtraction can be seen as adding with a part missing, can't it? Subtraction is just adding. That's a good way to bridge, like when you first tell kids about adding, and they've got it down, and you go to this thing called subtracting, you can say, look, it's the same thing, kids. It's just adding where you're asking for the part missing. That's what subtraction is. That's one way of viewing subtraction. Adding, subtracting are really the same thing. Do you know that all the operations all come from adding? I don't know if you know that. Think with me for a second about multiplying. Well, so we got adding, subtracting. Let's go on to multiplying. What about 3 times 7? How is that really adding? I'm making the claim it's all adding. All of math is adding. How is multiplying really adding? Yeah, it's just repeated, isn't it? It's just 7 plus 7 plus 7. It's repeated adding. So we have subtraction is really adding a negative. Multiplying is just repeated adding. How about dividing? How is 10 divided by, let's do 10 divided by 2. How is 10 divided by 2, which we know is 5, how is that repeated subtraction? You heard of that before? We're going to get more into that later. I'm kind of jumping the gun here. One of our, in a week or two, we'll have a formal thing where we actually practice that. But just for right now, just quick off the cuff. How can I look at 10 divided by 2 as repeated subtraction?
You keep subtracting 2, and then every time you get it. You keep subtracting 2 until you get 0.
Yep.
And you count the number of times you subtract.
Beautiful. You should be a math teacher. That's beautiful. Yeah. It's just how many times can you subtract 2? How many times? Until you get 0, like you said. Until you get 0. How many times did I subtract 2? 5 times. Which is the answer to dividing, huh? So what have I shown? Dividing asks how many times you can take this out. We normally say, how many times does it go in? But it's the same thing to say, how many times does it come out? So dividing is really repeated subtraction. Another way you could say that, it's really repeated adding a negative. Why am I doing this? Because I wanted to show you that everything's really adding. All of math is adding. It's just fancier and fancier adding. Do you know calculus? I don't know if anybody's taken calculus or seen calculus symbols. You've seen this kind of symbol on something? That's the big calculus integral is what that is. See if I see it on somebody's calculus book. You know what that thing is? So I'm going to show you all of math is adding. Not just add, subtract, multiply, divide. I've shown add, subtract, multiply, and divide. Right? Even dividing is just repeatedly adding negatives. That integral, which means area under a curve if you've done any calculus. But you know what it stands for? What does it look like? Doesn't it look like it's an S? And it is. That's not just looks like, that's what it represents. It's a big S, big stretched out S, and it stands for the word, it's the S in the beginning of the word sum. What is sum? Adding. It's a fancy way, that is a fancy way of adding. Adding up area under a curve is what it is. Anyway, my point is, all of math is adding. All of math, without exception. It just gets fancier and fancier and fancier ways to add things. It's that consistent. The whole math world is adding. All right, so with that in mind, let's go back. So they're going to show us here, they're going to say, okay, let's connect some things here. They're going to say 17 minus z is 10. Write a related, a connected addition sentence. Well, you can see the answer right over here. 17 equals 10 plus z. That's another way to say the same thing, right? 17 minus what is 10 is the same as saying 10 plus what is 17. Does that make sense? It's a related math sentence. It's an adding fact that's the same as that subtracting fact. Just showing you how they relate. Here's another one. 6 plus 3 equals 9. So which one of these facts are, you check all that apply, you can see the three answers there, right? 9 minus 6, that's a related subtraction fact. 3 plus 6 equals 9. That's just, they just switched the order there. And 9 minus 3 is 6. Now, you might, if I was you, I'd be like, yeah, I see those. But why not the other ones? Like, why not this one? What's wrong with A? Let's talk about why the other ones are not good. What's wrong with A? I mean, that's a true statement. A is certainly a true statement. 3 plus 9 is 9 plus 3. But it's supposed to be an other member of this fact family. Well, in fact, they told you there's 3. That's a big hit. But you see, there's no 6 anywhere in there. That has nothing to do with 6 and 3 making 9, does it? That's like saying, giraffes have spots. Okay, yeah, they do. But what does that have to do? That's true, but irrelevant to the original statement, right? And the next one, 3 minus 6 is negative 6 minus 3. Again, where's the 9? That has nothing to do with it. This one is just not true. We don't want to go with anything that's not true, right? And this is not true. It's not even close. And that has no 9 in it. Make sense? So we're just doing the ones. There's just other ways. These 3 are all implying the same truth, that 6 plus 3 is 9, said a different way. All right, we're going to do some number line. These are all we call these models, ways of representing the idea of adding and subtracting. Because math is a sense in the end. So looking at this. So this fact, this little picture, number line picture, represents what statement? See what it says? See how it says 9, take away 3, leaves what? 9, take away 3, leaves what? That good? The next one, 3 and 6 make what? 9. So if I can help with this, the answer, 6, needs to be over here as the answer, doesn't it? The question mark needs to be the answer. So you all know, you can probably find out 9 needs to be the answer. And over here, again, 9 needs to be the answer. 6 and 3. Here again, 3 needs to be the answer. It's got to be that one. 9 minus 6. So just pictures to give a feel for what's happening with adding, subtracting. Models are useful when you teach math. Every now and then, I mean, you've seen me. I drew some base blocks for you every now and then. right? So I think that's a pretty good way to use models. In other words, pictures. By models, I mean pictures, physical things people can touch. You know, if we had more time, in fact, this is a college class, and so I just see you 3 days, 3 hours a week, and I need to cover a bunch of material. So I don't really have a lot of time to bring manipulatives like that, those base 10 blocks I brought, and pass them out and do all that kind of stuff. But if I was teaching in an atmosphere where I had the people every day, 5 hours a week or longer, you know, I would do that physical kind of things at some level, to especially somebody that was new to a subject, just to sink it deep within. You know how all that stuff they say about hands-on, you know, when we touch things, it sinks deeper within. We see pictures. Those are all valuable. I feel like a little bit of a hypocrite as a college teacher. I don't have a lot of time to do that kind of thing, and you're not newbies to this. So it probably isn't the main pedagogical technique I should use or will use. But I want to say, that is a good thing, especially if you're teaching kids who are brand new to add and subtracting. You should be showing them pictures, hands-on things where they can actually see and feel what's going on. That's what we're showing here. That's what a model is, something that physically shows the math truth that we're conveying. Because, you know, this is just symbols. If you just take a kid and just write that, you mean like, why is there a dash in the middle? You know, what's that? Right? So you want to give them eventually the feel that it's like 6 objects, and you're going to take away 3 of them. See how that models this operation? Somebody can look at that and see 6 dots, 3 are being removed. Right? So that's a model. That's what we would call a model of the math truth. All right. All right. See how part C is always true? Let me make that a little bigger. So here it is. It's Z times 5 plus 3 is Z times 5 plus Z times 3. That's not just true for one particular value of Z, like Z can be 2 or 3 or 4 or whatever. Z can be anything. That's true for any number Z, isn't it? What's that called? Yeah, we just distributed. We just multiplied. That's a true fact for any number. Whereas like part A, I don't know if you can see part A up there, 3 times Z is 15. That's only true when Z is 5, right? Part A is only true when Z is 5. But part C down here is true for any number. We'll make that true. All right, we're just seeing if you remember the distribution property. Okay, they're asking, determine whether the following sets are closed under multiplication. Kind of weird language. And they're saying 0 and 12, is that closed under multiplication? What they mean is, if you take the set containing the 2 numbers, 0 and 12, those curly brackets just mean, that's a set notation. The collection of 0 and 12. So, is that set closed under multiplication? Meaning, it's closed under, why rewrite that? It's closed under multiplication when, sorry, I'm a little scribbly, when all numbers multiplied by themselves or other numbers in the set produce answers still in the set. It's closed. No, it doesn't get out of the set. So that's what it means to be closed. A system is closed if you multiply numbers times themselves or times other numbers in the set and they never get out the door. They never get out of the set. So, if you multiply 0 times itself, 0 times 0 is 0. That answer's in the set. 0 times 12 is 0. That answer's in the set. What answer's not? You can see the answers. No. What gets out of the set? 12 times itself. Yeah, 12 times itself. 12 times 12, 144. That's not in the set. So that system is not closed under multiplication. There's a way out for multiplication in that set. Let's try the next one. 6, 12, 18. Is that closed? You see the answer is yes. Do you see that's true? First off, do you see the pattern they're talking about? Let me write it out. 6, 12, 18, dot, dot, dot. What do they mean, dot, dot, dot? What's the pattern? It's adding 6 each time, isn't it? 24, 30, 36, 42, 48, dot, dot, dot. It's just adding 6 all the way. Just keep adding 6, adding 6, adding 6. So is that closed under multiplication? Meaning if you multiply any two of those numbers, is the answer still in there? Even a number times itself. Is the answer always still in there? You can see the answer is yes. Try any two you want, like 6 times 12. What's that? 72. Is 72 in there? Yeah, if we kept going. I don't know if we want to do much more of this. But 54, 60, 66, 72. There it is. Yeah. How about 6 times itself? 36. Yep, there it is. If you multiply any of those two numbers, the answer will still be somewhere in that collection. That's a closed set. How do you prove that? Like, how are we sure? How do you know there isn't like 66 times 72? Some gigantic number. How do you know that's still going to be in there? How do you know that's going to be somewhere down the line? Well, that's actually I'm asking too hard of a question, really. That requires a formal proof. That's why in math we use letters. You'd have to prove that's always true, you'd have to use letters. Because if you prove something true for letters, then it's true for any number, because a letter could be any number, right? So anyway, yeah, so pretend I didn't say that. It's a deep, we're just going to say it looks good, it looks pretty good, I hope it's true. And we're not really proving it's true. I'm tempted to try, so I probably won't be able to do it. Here, let's do the next one. And maybe if we have a moment, I will show a quick proof, if I can think of one. Coming down here. Is that one closed? You see the answer is no. Why not? Oh, no, it's yes. Let me think. It's yes. So is that one? They're just adding 2 every time. Adding 2 every time. Why is that one? I bet you can supply a good reason for that one. Why is that one closed under multiplication? Any number times, like 6 times 8, 48. Why is 48 for sure going to be in there? Because it's even, huh? Right? Do you see how this has all the even numbers 6 and bigger? You see that? And an even number times an even number has to be even, doesn't it? So yeah, there's no way you're going to get out of that set. Because you're just multiplying even numbers with even numbers, huh? So it's got to be in there. It's closed. That's basically how you would prove this. These are all things times 6, aren't they? This is 6 times 1, 6 times 2, 6 times 3. They're all what we call multiples of 6. So if you multiply 2 things that are multiples of 6, the answer's got to have a 6 in it. So yeah, it's got to be in there. That's basically the proof for part B. So yeah, those are closed. That making sense on that? Okay. So let's look at number 10. So go ahead and read that. See if it makes sense for you. Give you a second there. So if 5 is removed from the set of whole numbers. Now what's the set of whole numbers? Yeah, maybe I better be clear with that, huh? What is the set of whole numbers? What do we mean when we say whole numbers? No decimals, right? No fractions. It just, it starts at 0, 1, 2, 3, on you go. No negatives either. Whole numbers don't include negatives. Do you know what the set of numbers including the negatives is? What's it called when we put in like -1, -2, -3? It's called the integers. We'll get to that later. That's the integers, which include the negatives. So for now, whole numbers. So that's all we're talking about. So 0, 1, 2, 3, etc. So if you take 5 out, if you say, okay, I've got all the whole numbers except I'm skipping 5. Bye-bye 5. 6, on you go. But no 5. would it be closed with respect to addition? Now we're talking about adding, meaning if you add any two numbers in there, will the answer still be in there? Well, obviously not. 2 plus 3 is 5, for example. And you said 5's not in there. So it would no longer be closed. Right? You with me? And then number 5, if 5 is removed from the set of whole numbers, same thing, is it closed with respect to multiplication? So if you yank 5, same thing, we're taking, 0, 1, 2, 3, 4, 5, taking out 5, we got the rest of them, and we're just going to multiply numbers with numbers, and we want the answer to be in there. Would the answers always be in there still? What do you think? Well, it's yes. It's yes. It would. See, there's no problem with multiplication. See the difference between A and B? A was with adding. Yeah, if you're talking about adding numbers with numbers, you take out 5, you're no longer closed. You can get the answer 5, which is no longer in the set, so you're not closed. But here, on part B, if you're talking about multiplying numbers, you multiply a whole number by a whole number, you're going to get another whole number. What about the 5? Isn't there any way to multiply and get 5? Not unless you use the 5. And we can't use the 5 because he's not in there. What if they took out the 6? Let's change the question. What if they took out the 6 instead of the 5? Would it be closed now under multiplication? No, because what times what? 2 times 3, right, would be 6. So there's an answer not in the set, not closed, right? But 5, if you take out 5, it's still closed. Why? What's special about 5 that you take him out and it's okay? What's that? What was that answer? Because it's odd? Odd, maybe. How about if we had 21 and I took out 21? Would that be closed? No. 3 times. Yeah, the problem is the specialness of 5 is that it's prime. Prime. Do you know what prime means? Yeah. Nothing else goes into it but itself and 1. That's going to be our main topic on Friday. Prime numbers and how all the numbers are made out of primes. How are we doing? Plus D. Do you remember from your algebra days how you multiply numbers with a couple parentheses like that? Yeah, so it takes turns, right? So this first one goes to both. Right? So the A has his turn. It's parentheses, so it's going to be multiplication, right? And he's going to go to both of them. So A times C plus A times D. He's done. So the first to both. And then when he's done, the second one will go to both. Plus B times C plus B times D. And that's what they have there. Now, some people write that as FOIL, which is totally fine. FOIL stands for what? First, outer, inner, last. That's a nice way to remember it. Whoops, doing double O's there. First, outer, inner, last, which means the first one in this parenthesis times the first one in that parenthesis, that's what we did. Outer means the 2 outside guys, A times D, that's what we did. I means the 2 inside guys, B and C, that's what we did. The last means the last one in this parenthesis times the last one in that parenthesis. That's what we did. So it's just another way of saying the same thing. FOIL is the same thing I usually just say when I teach algebra. I just say the first goes to both, and when he's done, the second goes to both. First to both, second to both. Same thing. All right, we are at